Hello, everybody. My name is Zhou. A quick introduction of myself. I've been in this space about 7 years. Before that, I was a software engineer at Facebook, working on their infrastructure. So that's why I'm particularly interested in Ethereum infrastructure, especially Layer 1, Layer 2, DA, get a couple of supports from Ethereum Foundation, including personal grant from Vitalik, and also issue storage. That's a Layer 2 solution to scaling Ethereum, and also a couple of grants for OPStack. So today I'm going to share some of our work on Ethereum Layer 1 scaling, especially with some latest technologies called block level access list, which enables parallel execution, and also EVM compiler, which is able to compile the EVM contract code to the native code and then execute directly, with some experimental results on Go Ethereum. And the ultimate goal is try to answer the question that can be achieved 100x block gas limit of current Ethereum. Right now it's about 45 million, but we want to achieve 100x in the future Ethereum scaling plan. So especially from the execution side. So there's one big change of Ethereum roadmap this year is that Ethereum is not only trying to scale their layer 2, but also aims to scale the L1. In order to address a couple of issues in terms of, for example, liquidity fragmentation, and also some incentive alignment issue that a lot of people are discussing. So the near plan is to increase the gas limit, which is basically adopt a big block philosophy, so that we are able to increase this gas limit from, for example, 36 million to 46 million. Actually, it is now running in this with this number, and there's a concrete plan to increase this number to further to 60 million or even 100 million. And so the question is, with all these near plans, what is the ultimate goal that we can achieve with Ethereum current, for example, execution, EVM smart contract, and also, for example, MPT, the tree. And what is the ultimate boundary of the Ethereum L1 block limit? For example, suppose if we want to achieve 100x, that means that we need to have 4.6 giga gas per block. So this is a pretty large number. I will explain later. So before we dive into the real number, let's look at how the current situation is. So this is one gas that latest gas I run on top of a pretty powerful machine with 16 cores and also RAID 0 NVMe SSD. And so it can achieve about 300 megagas per second. Actually, there are optimization has been done recently. So actually early this year is about 150 million gas per second. So it's about twice because recent optimization. However, the Ethereum consensus require all the nodes can validate the corresponding execution result, which means that it has to up to 4 seconds to verify all those transactions and sign, and also be able to broadcast and also sign the corresponding attestation in the following time slots. So which means that we can have up to 1.2 giga, which is 4 times 300. That's clear. So that is the current limit of the, especially for Go Ethereum client. And for other clients, maybe a little bit better, but the number is also very close. So which means that we are only about to support 12,000 Uniswap V2 swaps per second. So which means that we're still a little bit far away from the ultimate goal that we can scale Ethereum 100x on layer 1. So one quick question is that, can we also rely on Moore's law to basically increase these limits, just sleeping on our bed, and then the hardware will automatically accelerate all the execution, and also both in terms of memory and disk and also bandwidth? The short answer is no. The reason is that the Moore's law is not yet working these days. Everybody knows that the frequency of our CPU is capped by about 4 gigahertz around 2005 year. The reason is that we cannot build such small number of the some limits or physical limits of those transistors. However, another observation is that we have called modified Moore's law, that showing that if we take into account the number of cores per CPU chips, actually it still applies. So this is a multi-core area. Actually, the line is still almost double in 18 months. And so what that means that we are able to also employ this modified Moore's law to also improve the EVM execution. Unfortunately, it's not, because EVM execution is just sequential, which means that we can only harvest the benefits before 2005 because of the CPU the speed limit. So because of this, Ethereum Foundation also called developers thinking about how to employ the multi-core processing to improve the Ethereum EVM execution performance. So the most recent update is called block level access list. It was introduced in EIP 7928. Actually, 2 years before, we was proposed a similar idea via a ESP academic grant to say, hey, we should investigate how we are able to parallelize EVM execution. Actually, our idea at the time is not only be able to apply to layer 1, it can also apply to layer 2, so that both layer 1 and layer 2 can benefit from this multi-processing. So the general idea is to add a called access list in the Ethereum block to tell what are the locations of all the transactions we'll access in this block, including the address, including the slots, the storage slots, and also may include the corresponding value. For example, what's the value corresponding to those locations. So the benefits of block level access list is that because we are now running the Ethereum in a sequential way, so there's a significant latency from the I/O readings, because every time you just issue one I/O, wait, and then wait for the I/O back. So in the early result, actually this is the result of the early this year, is that 80% of the EVM execution that is waiting for the I/O response. So that takes a significant amount of the EVM execution. So at the same time, actually the modern disk, like for example, this is just a disk that with about $100 can easily offer like 10s or even 30s parallel IOs without sacrificing just a small sacrifice of the latency, but almost retrieve a really high bandwidth. Actually, this can be even more, but just for the illustration purpose, like we can actually issue much more parallel IOs. So, which means that if we are able to fully utilize the parallel IOs, then we can easily achieve 10 times or even sometimes 20 or 30 times improvement on the EVM execution on reading IOs. And so with the introduction of the block level access list, so a significant change is that now we are able to using the BIL information so that we can first read all this data parallel from the database, so that we can almost, I will show the data later, eliminate corresponding read IOs in the EVM execution. And second, with a slightly improvement of this BAL, we are also able to run those transactions in complete parallel. So for example, suppose we are able to use, for example, 60-core CPUs, then we are expected to achieve 10 times of performance using just very widely adopted like commodity PCs. So we implement all these ideas on top of Go Ethereum, both in terms of parallel I/O and also parallel execution, and then we study how much performance improvement can be achieved using these ideas. So it's using pretty latest machine and with a very high performance SSD. And also we make sure that every test is fair, so have to clear page cache, and otherwise the cache may speed up the corresponding results or the second results. And also the key result is that, so if without, for example, the BAL with parallel IOs, we can observe that the IO still takes a significant time. That actually is the optimized Geth which takes about more than 50% of the execution. So with the parallel IOs, we can reduce this number to less than from 1 to the 10x, and right now the number has become less than 10%. And at the same time, so this is still experiment on sequential execution. So the execution now becomes the biggest part of the EVM block processing. So the next experiment is to using parallel execution with some additional information of block level access list, so that now we can parallelly execute those transactions and further reduce the time. Right now we can achieve about 6 seconds in 500 recent produced blocks. And so with all this, we also do some experiments. Especially we found other parts of the EVM execution that is mainly to calculate the local root of the execution, so that we are able to recompute the hash root of the world hash, which will take a significant time. We then say, hey, whether we are able to amortize those costs by using large number, that's 10x block class limit. By basically, the simple idea is just aggregate 10 blocks. So rather than verify their hash roots for every block, it will basically verify the hash root for every 10 blocks, and then amortize those costs on the hash root computation. And then we are able to achieve currently 1.2 gigagas per second, which times 4, which means that we are able to use this technique. We are almost be able to satisfy the 100x block gas limit of current Ethereum. So this is a pretty amazing result. So besides block level access list, we are also considering another further question. Question is that, can we further accelerate EVM execution? Because now this part seems to become the bottleneck. Recently, there are a couple of the latest ideas that is flying around in the Ethereum ecosystem. So one direction is called RISC-V, which basically to using the RISC compile the smart contract into RISC-V OP code and then run natively on some machines. That means that we need to transpile existing EVM bytecode and also need some new gas metering. The big direction is to still support the EVM as the execution engine, and then compile them to the native code, for example, x86. So there are a couple of famous ones, for example, EVM-C, EVM-1, and also EVM MLRR. And unfortunately, when we are trying to evaluate the corresponding result on top of gas, we cannot find the handy compiler, EVM compiler for gas. That's why we create called Go EVM-C, which is an EVM compiler that can be used by Golang, for example, Go Ethereum. So that now we are able to compile smart contract into LLVM-IR first. That's the intermediate representation, and then convert it into local binary so that we can achieve the native performance on top of our local machines. So this is an example of how the intermediate representation in the LL format looks like. And so the couple of design goals. So first of all, we can be compatible with gas so that we are able to easily be integrated with gas to evaluate all the performance. And also it is able to minimize the recompile cost for EVM upgrades, especially if we implement all these we call unstable OP codes, then we have to recompile them every time. And so and also in terms of optimization. So we just open source the repo, and our performance is pretty promising these days. We shows that compared with the Go Ethereum, we can achieve about, so this is the Go Ethereum, this is our optimized result, about 3 times performance improvement on top of Fibonacci sequence computation. Okay, since we have a limited time, I will skip some slides and future work. So really happy to share our our recent work on all those Ethereum optimization, and also would like to answer some questions if you have. Thanks.
Yeah, I guess this approach is a little bit in tension against, having people be able to prove on a mobile device or something, like sort of light clients and stuff like that. How do you, I mean, if someone were to run this, they need that super fast computer, very expensive. How do you see that, those two kind of goals coinciding?
Yeah, so actually there's more precisely, that's called ZKVM that aims to basically do the off-chain proving and off-chain computation, and then be able to prove easily on top of even on a cell phone or any other like mobile devices. So I think there's a lot of involvement. For example, if they recently had a called link consensus, which one of the tasks is to try to achieve that goal. But for near short term, actually, still like Ethereum, if we want to be able to immediately, about 1 or 2 years, to be able to increase this capacity to 10x or 100x, this is some technology that we should adopt. And second is that even compared to cell phone, is relatively more expensive. But all this, for example, this experiment built on top of, we are built on, is about $100 per month machine.
Oh, okay.
Which compared to the validator cost, which is 32 Ether, that is almost
I was somehow getting the impression this is gonna, you would cost $20,000 setup to run a machine. So,
No.
but in order for this to work, all the clients would need to be running this instead of, like, they would need to have a certain spec machine. There would be sort of a minimum spec machine they would need to run, right?
In order to use all this. Yeah, so all this upgrade spec will be incorporated into all the clients.
Yeah.
So that's why there's other clients, for example, RAS. So RAS, Zig, they are also implementing their features. But the point is, like, to our best knowledge, we are the first one to evaluate this comprehensive results on top of Gold Ethereum, which is one of the largest client on the adopted by the other people. So yeah.